Hello, everyone. Thank you for joining me on a Saturday afternoon. Hopefully, this is worth your time on the weekend. I'll try to do my best to make it so. I'm Mustafa. I'm a research scientist with the Red Hat AI Innovation Team. And today, I want to go through and talk about language model post-training. What does that mean? What does that look like today? And how can you get started with it? Now, just a quick disclaimer, this is going to be a very dense talk, and I'm going to cover a lot of topics. So if you find anything I talk about particularly interesting and you feel like you'd like to go more in depth on it or you'd like to learn more about it, feel free to find me afterwards. I'm happy to talk more about it with you, and I'm happy to point you towards resources and help anyone get involved with their post-training journey. So without further ado, let's go ahead and get started. So before we go into post-training, I just want to talk a little bit about language model training basics. So the world of training language models is essentially split into two buckets. There's pre-training and there's post-training. This talk is going to be focused a lot more specifically on the post-training part of models, but before we get to that, I'm going to do just a brief crash course on what pre-training is, just so you know what we're starting with when we get to the world of post-training. So to begin, every model can essentially be thought of like an empty brain. It's a set of randomly initialized weights that hasn't learned anything, hasn't seen anything, and isn't going to do much for you. So what we're doing during pre-training is we're basically just trying to fill this brain with all of the useful available information across a large number of domains that we can, such that it can make connections between these domains, hopefully form and learn enough knowledge necessary that it can then be translated into any downstream tasks that we're interested in. So right now, we're not concerned with how we're using the model. We're not concerned particularly with how we're inputting and outputting. We just want this model to learn as much as possible, about as much as it can. So how does this work? To start, every model begins with a vocabulary. This is a set of interpretable subwords or tokens that it can use as input and output. So the model is going to take tokens or subwords in your vocabulary as inputs, and it's going to in turn produce subwords or tokens as output. So this is the key when it comes to any sort of language model usage. Tokens in, tokens out. And in fact, that's all we're training a model to do. When we pre-train a language model, the task we're focused on is simple next token prediction. So what that means is for all of the data that we have across our vast corpora, we just wanted to learn to predict each and every token given all the tokens that came before it. So looking at the example, let's say we have the sentence, "The dog eats the apples," in our data set. What's going to happen is that's going to be translated into tokens. Now, in this case, it's pretty clean. We've got a token per word. In reality, it's going to look like the top right, where you have much less readable subwords. But what we're going to be doing during pre-training is take that sentence and say, given the, learn to predict the word dog. Then, given the dog, learn to predict the word eats. Given the dog eats, learn to predict again the, and so on and so forth. So we're just going to follow that process throughout all the data that we have. And what's the goal there? So the idea is that we're trying to build a probabilistic model across all of our data. The goal is to predict what word comes next given a set of words. So for example here, we have the tokens 1, 2, 3, Our model should then be able to predict a reasonable next token. In this case, it says there's a high probability that the next word, given the data I've seen, should probably be 4. And that's the goal here. We're just saying, given a set of input words, what is the most probable output word across all of the data that we've seen? That's pre-training. So what we're doing here is we're just learning the language that we've outlined in that vocabulary. How do we form connections between those subwords in order to put together common coherent patterns? How do we form relationships between those words and make connections such that we can produce intelligible outputs that can then be useful for tasks? That's the goal with pre-training. So now we've got a model with the basics of language down. It can form sentences. It can predict words. Well, what can we do with that? How do we actually utilize that? Now we get into post-training. So, post-training is the answer to how do I make my model useful? If we need our model to be able to answer questions, follow instructions, fulfill requests, talk about specific domains, learn more in those domains, improve in reasoning and logic, respond safely to input queries, all of that falls into the world of post-training. So, first, we're going to start with the most basic form of model post-training, which is supervised fine-tuning. Here, it's a very simple task. Given an input sequence, we want to learn to produce an output sequence. Here, we're saying what is the capital of France, and we want our model to learn to say the capital is Paris. We're going to mask that input sentence. It's going to be used as a condition, and it's then going to learn a set output sequence. So we're going to give it that full input, what is the capital of France, and it should learn to then say, the capital is Paris. So we've got a problem. That format doesn't really make sense outside of a single participant. All we've taught our model is to learn to form sentences, to copy documents. It doesn't have any way to actually track who's saying what. And so we need a model interpretable format to distinguish between participants in a conversation. We need to be able to understand what was given as an input by a user and what's an output that the model is actually responsible for generating. We need to know what to learn and what's given. So this is where messages formatted data comes into play, and this is the key when it comes to supervised fine-tuning a language model. So often referred to as instruction tuning or multi-turn chat tuning, each message, either an input message or an output message, is going to be tagged. In this way, we're formatting our text more like a dialogue instead of a document. So here, we'd actually label, the user said, what is the capital of France? The assistant or the model generated, the capital is Paris. The user says thanks, so on and so forth. We outline our conversation. So how do models actually understand this under the hood? Well, models operate with what we call special tokens. These are specific tokens in the vocabulary designated to highlight the beginning of new messages. So in this case, when we input to the model, we'll have a user token followed by the condition, what is, so on and so forth, and then an assistant special token followed by the desired generated output, the so on and so forth. So this allows the model to understand the concept of participants, and more importantly for us, allows training libraries to understand what parts of your data need to be learned by the model and what parts are going to be expected from users. So now, of course, we've got another problem. Special tokens and formatting varies model by model because it would be way too convenient if every model followed the same format. To give them credit, it does actually matter a lot depending on the purpose of the model or the capabilities of the model. Different formats and different special tokens are going to work better for different purposes. And so each model that you'll find on Hugging Face will likely have its own special tokens to denote these message breaks. It'll have their own format for their data. How do we handle that? Because obviously as a user, you're not concerned with this. You're never typing yourself like !user and !what is, so on and so forth. Well, the solution there is to actually have a model-included translation layer, what we call a chat template. So what happens is, when we tokenize your input, we're also going to apply this model-specific chat template to translate it from your raw input into a tokenized message that follows the format with special tokens included of the model you're working with. So here, if you give us what is the capital of France, we will then translate that into user, what is the capital of France, assistant. And this assistant special token will tell the model, all right, it's your turn to generate. And so when we're post-training a model with supervised fine-tuning, this is the key difference. The data that we're going to pass in is going to be messages format. Each sample will be like a line in a JSON-L, and it's going to have a list of dictionaries containing the role and the content of each message. So a sample here that we'd pass to our model would be like role user, what is the capital of France? Role assistant, the capital is Paris. So now we can do a lot to actually get our model to generate various outputs given inputs. And it can follow multi-turn conversations. So we can teach our model to do some of the things that I've outlined before. It can fulfill requests, it can follow formats, it can answer questions, and so on and so forth. But now, let's move into the world of continual learning, another post-training option. So what happens if we want to teach an already fine-tuned model something new? What happens if we want to continue training on either the same information that we've already been training the model, or if we want to introduce entirely new domains into our model? Maybe we might want to iteratively add new knowledge, or we might want to keep updating our model with periodic data over time. Say you've got annual financial reports that you need the model to keep up with, but you also don't want it to forget what it learned before. So this is a big problem when it comes to supervised fine-tuning, is forgetting and overwriting. You see, when we do supervised fine-tuning, we're actually updating the full set of model weights. The more you're adding to your model, the more you're forgetting the old information because you're actively overwriting the entire model. So how do we solve this? Well, currently there's a lot going into continual learning research, which means methods that are aimed specifically at solving this problem of minimizing forgetting and keeping the general quality of your model high while you introduce new data. So for this talk, I want to talk specifically about a method called orthogonal subspace fine-tuning, or OSFT. So OSFT is a continual learning method aimed at reducing forgetting by targeting the least important or least contributing weights in a model. So ideally the weights that contain the most redundant information or have the least impact on producing your outputs. So how this works is it's utilizing adaptive singular value decomposition to try to identify high-rank components to keep frozen in the model and leaving low-rank subspaces unfrozen for training. So to explain in a little more detail, how it works is we're going to look at each weight matrix in your model and break it down into components ranked by importance. So for the high rank or critical components, or the top singular values when we perform SVD and their corresponding directions, these capture what we believe is the most important patterns the model learned for previous tasks. These are the components in your matrix that have the largest effect when taking in an input and producing an output. There's then the low-rank components, which are the smaller singular values that represent less critical or redundant information. So we're basically going to take all your weight matrices and try to split them up into, this is the portion that's really important to maintain for your model's quality generally and its previous learned tasks. And here's the portion of the weight matrix that isn't really contributing much or might contain a lot of redundant information. So we know that this is space we can more safely write into in your model. So how this works in practice is you essentially set a threshold, say keep the top 80% of singular values as critical directions. Then, during new task training, we're only going to allow parameter updates in the directions that are orthogonal to those critical directions. So basically, the remaining lower rank subspace that we left unfrozen in the model. So this means for us that the model is still going to be able to learn the new task that you're interested in, but only in that leftover parameter space that we know won't mess with the critical information that it's already learned. So what you do in practice is there's a field, an unfreeze rank ratio. This is going to determine how much of the original parameter space you reserve as critical and how much you leave available for new learning. So this is kind of a balancing act that you have the power to set yourself. For example, if you set this unfreeze rank ratio all the way to 1, then you're back to doing regular supervised fine-tuning. All of your weights are unfrozen, you're updating your full model, you're giving the model maximum capacity to learn the new task at the risk of forgetting a lot of information. On the other hand, if you set it all the way to 0, your model's fully frozen. You're not going to lose anything, obviously, because you're not gaining anything. And then if you say in the middle, you set an unfreeze rank ratio of 0.5, now half of your model, what we believe is the most critical half, will remain frozen, while the other half will remain trainable. Now, if you find in this scenario, hey, my model's not learning enough, you can increase the unfreeze rank ratio to give it more room to learn. On the other hand, you might say, hey, it's learning my task really well, but I'm forgetting a little too much. You can decrease the unfreeze rank ratio to make sure more remains frozen. And so based on your task, if you need to give more room to learn or you need to give less room to retain more information, you can move this field up and down between 0 and 1 to dictate what balance makes sense for you. Now, what we just talked about was a parameter-efficient method for fine-tuning. Now I want to go a step further into other classical popular parameter-efficient methods if you want to go really small with your memory footprint. So let's say we actually want to keep our entire model untouched. Instead, all we want to do is adapt the model slightly for a given use case. So we want to make small adjustments such that maybe it handles a specific format better, it adapts to giving a specific output more properly, it can match kind of the format or the fields you need necessary for your outputs, it can maybe better understand the question you're asking or the grammar with which you're using. These slight adaptations or adjustments to your task, assuming the model already has all the information it needs to perform your task well. This is the goal for parameter-efficient fine-tuning. So, a couple of popular methods. The first and most simple parameter-efficient method is prompt tuning. So what we're doing is we're adding a trainable soft prompt, which means a fixed length sequence of vectors, or you can consider tokens, that we're going to append to any given input. So think of this like a system prompt or an instruction that instead of hard coding or engineering yourself, you're asking the model to learn, and it'll then be appended to all of your inputs. That's prompt tuning. So simply learn the best instruction to give my model while working on a certain task. Taking it a step further, a very popular method that a lot of you might have heard of before is low-rank adaptation, or LoRA. What this means is, instead of just adding a soft prompt, what we want to do is target components throughout all of the model layers and add an extra set of parameters that we're training with a much smaller footprint than the original model size. So what does that mean? How does that work? When we train a model, we are updating a set of weights in every given weight matrix. Instead, LoRA says, what if we approximate that weight update with low-rank components? This works because, well, matrices can be decomposed very easily into low-rank components. So for example, let's say I have a weight matrix W that's a 4x4 matrix. When we want to update that with full fine-tuning, we'd be adding a 4x4 delta, a change on top of that weight matrix. Instead, LoRA says I can decompose that 4x4 delta weight change into a matrix A and B that when multiplied together make the same size as the original weight update. But instead, I only need to do 2 4x1 matrix updates instead. We're effectively converting the training task from an O of n squared to an O of 2n here. Now, it's important to note this is an approximation. So we're giving the model less space to learn. We're saying we can probably learn what we need in these two 4x1, 1x4 spaces, apply it back to the 4x4 space, and that should be enough information. Now, you can customize the rank and say, hey, maybe I need a 4x2, 2x4, give it more room, 4x3, 3x4, so on. So LoRa gives you this parameter efficient approach to which you can approximate model updates and then apply them back to the original model. So there are a lot of interesting extensions to LoRa. If you're interested particularly in these parameter efficient techniques, I suggest you also take a look at QLoRa, which uses quantization to further reduce the memory footprint for LoRa training, or OLoRa, if you're interested in kind of the state-of-the-art of LoRa today, which leverages orthonormal matrix initialization through QR decomposition. I won't go too much into it today due to time, but if you're interested in LoRa, highly recommend you check out these methods as well. With that being said, I want to move on to the next pillar of post-training that's very important these days, and that is reinforcement learning. So, reinforcement learning. What is it and why do we have it? Basically, reinforcement learning allows the model to explore a given environment and find the optimal path to a solution itself rather than trying to hard code or prescribe a path to a given solution. So the basic flow is as follows. You have an agent in an environment, or in this case, let's say a model, and it's in a given state. Based on that state, it'll take an action. Based on that action, it will then receive a reward as well as an updated state. And then it'll begin that cycle again. So the easiest way to think of it is take chess. You've got the board state in chess, and your model says, I'm going to take an action, which is move a piece. The model will then receive a reward based on how good or bad that move was, as well as the updated state, the new state of the chessboard. Then it'll take another action, receive a reward and an updated state, and so on. And so the core goal of reinforcement learning here is how do I get my model, given that reward, to make a better action the next time, and a better action the next time, and ideally learn what are the best actions that I can take given my state. So that flow of given a reward, learn how to take a better action is the core of reinforcement learning. So why do we care? Well, reinforcement learning gives us a room for guided exploration, where it allows the model to find the correct line of reasoning within its own distribution in order to reach the correct output. So rather than trying to force our own solution path, our own reasoning thought, our own chain of thought step-by-step approach that might not be in the model's distribution or might not make sense for what it's learned, we are going to just try to sharpen the model's distribution, hone its thinking skills, hone its reasoning skills to, given all the paths it could take to reach a solution, try to find the best one. And this helps a lot for tasks like reasoning and math performance. It helps a lot for alignment because it'll follow maybe the safest path if you're interested in model safety. It helps with preference. If users have certain preference when working with a model, it'll follow the paths that best align with user preference and so on. So today I want to talk a little bit about reinforcement learning with rules-based verifiers. So what that means is for tasks like math, we can introduce a standard deterministic verifier to see whether or not a model answer is actually correct. And this allows us to very easily assign rewards to given solutions. So it gives us a feedback loop where we can kind of improve reasoning and accuracy improvement very quickly by saying your answer is right, your answer is wrong. So the most common way that's used today is with a method called group relative policy optimization, or GRPO. So given a model, we're going to say, generate a bunch of potential solution paths, or rollouts, as we call them. So take a bunch of different approaches. We're going to give it a high temperature, which means flatten the distribution out, add a lot of variance. And we're going to say, go in a bunch of directions, try to see if you can come up with a way to reach the solution for the question we're giving. So for example here, very simple question. We're going to say 2 plus 3. We're going to say, think about it. in however many different ways you can, try to come to a solution. It's going to say, hey, here's 7 different paths. In most of them, here are my solutions. And we're going to say, okay, we've got a rules-based verifier. So we can verify your math. We can say all of the trajectories, all the rollouts, where you said 5 were correct. So we're going to assign you a reward of 1. All of the rollouts where you said not 5, we're going to give you a reward of 0 because it was incorrect. Then what we're going to do is we're going to compute advantages. We're going to normalize these rewards in order to see how important it is to index into a given potential solution. So basically, let's say I gave the question, and it tried to think about the problem a bunch of different ways, and in like 90% of those cases, it was completely wrong, and then it followed one potential path to the solution and said, hey, this works, here's my answer. We want to say, okay, let's weight this path very highly and move the model further in this direction because we know this actually works. Most of the things you do don't work. This works. We want you to index more heavily into thinking like this for problems that are similar to the one you just tried to solve. Alternatively, we might say, hey, this was a simple problem. You took a bunch of different approaches. All of them actually worked out kind of well. So we don't want to bias the model heavily towards any given one. Instead, we're going to say, hey, all of the correct paths are open. We don't want to kill the model's creativity. We want it to be able to explore different paths still. And we'll say all of those were good. So that's the benefit of advantages. We're allowed to index heavily into hard problems where we find one right path. But for easy problems, we're not killing the model's expressibility or creativity, all while remaining in the distribution of the original model. So what this does is it allows us to increase the performance of the model, both in reasoning and in the verifiable task that it's trying to solve. It avoids random behavior and high variation on a lot of tasks, and it's aimed at reducing that variation and following the correct paths of reasoning to reach solutions without changing the model, introducing new information, or confusing the model. So this is the goal when it comes to rules-based reinforcement learning, like GRPO in this case. Now, there's a lot of room to explore, both in terms of reinforcement learning as well as other techniques in the post-training world. For example, if you did find reinforcement learning to be something you might be interested in, there are extensions today like Dr. GRPO and DAPO that improve upon GRPO. There's stuff like preference tuning, which you can do offline with methods like DPO. There's online methods for alignment like RLHF that are designed to get user feedback and incorporate that for preference tuning. So there's a lot to do in reinforcement learning. There's a lot to do outside as well. So other techniques in the post-training world that are very interesting today. Model merging is a very new topic that people have been exploring a lot recently, where you might fine-tune a model, take the original base model or a second fine-tuned model on a different task, merge them all together to try to retain performance while adding a variety of new tasks. There's also post-training model compression, which is a very interesting field these days. If you're interested in quantization, sparsification, and so on, exploring these areas for how do you pack a model as small as possible while retaining its quality. And of course, after training, there's the whole world of inference. So a lot to explore. If any of it interests you, I'm happy to talk more with you about it. For now, though, I want to go into how do you get started with post-training? How do you get started today? How can you access the algorithms I discussed, and where do we go from here? So now I'll take a few minutes to talk about the Training Hub. So the Training Hub is an open source library that we've designed to be an algorithm level abstraction for state-of-the-art post-training methods. This is an open source community project that supports multiple popular implementation backends for the algorithms that we're discussing. So it's available on GitHub. You can pip install it. There's a PyPy package today. And currently, we support SFT, standard SFT, and we are also, I'm proud to say, the first library to implement and support OSFT for continual learning. So if it's something you're interested in trying, this is the one place you can get it today. We're also working towards adding the reinforcement learning methods I discussed, the parameter efficient methods I discussed, and so on. So those interested in trying it out or contributing or working towards this progress of having algorithm level abstractions for the entire world of post-training, I encourage you highly to check it out and contribute if you can. So let's take a quick look at how it actually works. So getting started is very simple. We've abstracted it such that every algorithm I've discussed is represented as a simple Python function. So from Training Hub, you can import SFT, and then you can run SFT as simply as saying, I want to use this model, here's my data, here's where I want to save my outputs, here's how long I want to run. Now, if you need more customization, and I'm sure a lot of you will, there's a lot of additional arguments that are made available to the user. You can adjust the actual training dynamics, you can change your batch size. If you have memory requirements, you can cap your memory using max tokens per GPU. If you want a checkpoint at specific intervals, you can adjust that. And of course, if you're running multi-GPU or multi-node, we support it out of the box. Multi-GPU is as easy as changing the number, the nproc per node, and multi-node is as simple as setting the remaining fields in that distributed section, and then just running this function on each node that you're training on. Now, like I said earlier, we also support OSFT fully out of the box today. It runs the exact same as you would with SFT. You just use the OSFT function instead of the SFT function, and we introduced two new arguments. The main one is the one that I discussed earlier, that unfreeze rank ratio, to determine how much of your model remains frozen and unfrozen. And the second one is a memory efficient initialization of that weight matrix splitting process if you have memory constraints and you want to avoid any additional overhead. So both are available today. This is how we're going to surface additional algorithms as well. So let's say if you have GRPO, you have a GRPO function. LoRa, you have a LoRa function. All of them holding the same set of common parameters, as well as maybe one or two additional parameters that are specific to that algorithm. Now, if you're interested in seeing documentation and examples, notebooks, scripts, tutorials, and so on, we have them available in our GitHub here. And with that, that's post-training. So, if anyone has questions, I think we've got a couple of minutes left.
Mustafa, thanks for the very nice overview of post-training. For reinforcement learning, what exactly are you updating?
So reinforcement learning traditionally is also going to be updating the full model weights. But interestingly enough, because all of your data is in distribution, because the model is generating it itself, what we see is that it actually ends up targeting only very small and specific portions of the model. Because we're sharpening a distribution instead of adding new information, the updates tend to be much smaller in magnitude than with something like supervised fine-tuning. But by default, all parameters within the model are unfrozen and left open. There are some interesting extensions that are being developed today and that have been talked about recently that try to combine parameter-efficient methods with reinforcement learning, but starting point is fully unfrozen like SFT.
Thanks.
Thanks, Mustafa. Quick question. How do you identify which vectors to update and which vectors to...
For OSFT specifically?
Yeah.
Yeah. So for OSFT, we're using this method called adaptive singular value decomposition, or SVD. And the idea there is it allows us to have these singular values assigned to the components within our weight matrix. And high singular values correspond to the components of our matrix that are contributing a lot to changing the output of our model. So as the information passes through the model, when SVD assigns a high singular value to a component, that means that that component is responsible for a larger change to our output. Whereas the lower rank components, the lower rank subspace that we're leaving unfrozen, is having a smaller impact on the actual changed output. So that's kind of how we split it up. What it does in reality is it just assigns singular values, and we sort them high to low, and given that threshold, we choose where to cut it off for frozen and unfrozen.
So do you need a calibration data set for that?
No calibration data is necessary. This is going to be a direct analysis of the model weights themselves.
Thanks.
All right, looks like that's time. There's one more question, so I'll be able to talk to you outside to cover that as well. But thank you, everyone. Hope I made it worth your time this weekend. And